Over the last few years, I created a number of interactive web-based simulations and visualizations. Examples include neural cell automata demos, various particle systems, and other things. Although I really enjoyed making them, I was always annoyed by the verbosity and complexity of WebGL API that I was using. One needs to pay attention to shaders, render buffers, textures, uniforms, vertex buffers, and so on, to do even the simplest things. Often this stopped me from bringing new ideas to life. I always thought that there should be a more concise way of expressing the computation I was doing. This year, I started working on a minimalistic library built on top of WebGL 2 that tries to hide this complexity under a minimalistic interface. I called this library SwissGL because most of the tasks, whether it's a physical simulation or a mesh rendering, can be done by calling a single function that receives snippets of code that should be ran on GPU. I think of this library as an experiment rather than a final product, so expect many changes in the future. I also hope that some ideas may become useful in other projects, especially in the light of the arrival of the long-awaited WebGPU API. As of now, SwissGL consists of a standalone JavaScript file with about 700 lines of code, small documentation, and a set of usage demos that you may find at SwissGL website. Clicking the button in the corner opens the source code for a corresponding demo, and no demo has more than 100 lines of code. Most of the demos are various simulations. Others show how to render graphics primitives or process microphone or camera input streams. All demos should work on desktop and modern mobile devices, and some support virtual and augmented reality through WebXR API. Today I'll show how to use SwissGL to implement and animate a scientific diagram. This video was inspired by the beautiful tutorial Artem Kirsanov released on his YouTube channel. As an exercise, I decided to reproduce the branching neuron model animation presented at the end of his tutorial. In the spirit of minimalism, the only tools I'm going to use are SwissGL JS and the Chrome browser. So let's start with an empty browser window. First, I will download SwissGL library file. I'll go to GitHub. I'll create a new folder for this tutorial and put the JS file there. Also, I will need a minimal HTML boilerplate that uses SwissGL library. Let's rename it into just index.html. Now I opened the local file and it loaded the local version of SwissGL library. I prefer to copy SwissGL to new projects because this way I'll be sure that those projects will not break if I make changes to the library on the GitHub. Now I will open the developer tools by pressing F12 and navigate to Sources tab. Now I need to give Chrome access to the folder I created so that I could edit files right in the developer tools. So here is the SwissGL library and here is the minimal boilerplate. I will increase the font size a little bit. And we are ready to start playing with the library. So, for example, these 3 lines render this spiral effect, and if I remove it, save the file with Ctrl or KMD-S and refresh the page, I will see a blank screen. This line creates a SwissGL context given the canvas. Internally it creates WebGL2 context and augments it with some other data structures. Then this is a helper that creates a render loop that runs 60 frames per second, and this is a helper function that makes sure that canvas WebGL size matches the dimensions of the canvas in case page gets resized. In its heart, SwissGL is a tessellated plane rendering library. So everything we're gonna draw or simulate will be composed out of those planar primitives rendered into various buffers with various shaders on top of them. Let's render our first quad. GLSL function has one or two arguments. First tells what and how are we going to render, and the second specifies the destination. We will get to the second argument a little bit later. First, we create a dictionary with a bunch of parameters. The most important is FP, which is a fragment program that is going to apply to the pixel of the rendered quad. Let's just pass a string containing number 1. Now we drawn the full screen wide quad. We can pass 0.5 and we have a grayscale quad. We can also pass a total of 4 numbers. We may assume that whatever expression we are going to put here will be wrapped in a vec4 constructor and emitted from a fragment program. There are also some special variables that are available to us. For example, we can get UV coordinates of the current pixel. So red maps to X coordinate and Y maps to green color. We can also have similar coordinates, but spanning from -1 to 1 instead of from 0 to 1. So if I take absolute value, I will see that 0.00 is right in the center of screen. We can easily pass uniforms to programs that run on GPU. For example, we may want to use time in a fragment program, so we just add it to the parameters dictionary, and then we can use it right in the code here. So now blue channel depends on current time. We can also use JavaScript syntax sugar to pass variables from local context, even in a more concise way. When a second argument is not provided to GLSL function, it renders primitives on the screen, on the canvas that was used to create a SwissGL context. But we can easily render to an off-screen buffer. We need to provide the second argument, and this could be either an existing render target, or we may ask SwissGL to create a new render target in place. So we can provide size. For example, I want to say 10 by 10 texture, and when we create a new render target, we need to provide a tag. This is needed so that we could create textures in place right where we use them, and then even this line is going to be called at every frame. At every next frame, the SwissGL will understand that this texture is already created and will reuse the existing buffer. So we return this texture, and we can render its content on screen just by passing it as a uniform, and reuse this uniform in a fragment program. So we are sampling texture using UV coordinates. So now we see that this texture is very pixelated because we are using very low resolution for this render buffer. In place texture creation makes it easy to work with textures that may change their size, for example, depending on screen resolution or some program settings that don't change very often. For example, by default, when we remove the size parameter, the newly created texture has a resolution that matches the screen. We can also provide the scale parameter, for example, make it 1/32 or 64, and now we have a texture that has resolution depending on the current render buffer size. So when we resize the canvas, the texture automatically gets resized according to the needs. For example, it's useful when you need some auxiliary buffers which have resolution depending on the screen size, and that needs to be adjusted with the change of screen size. Also, when we look at the console, we can see all the objects being created for us. So this is auxiliary buffer that is used to pass geometry to GPU. Then there is texture that was created, and two shader program, one to render into the texture and another to render primitives on screen. In addition to X, Y, or UV variables that specify current pixel positions, we may use, and it's very convenient to use I input variable that specifies the integer coordinates of the current pixel. For example, we can use this variable to render a beautiful bit field effect. So now every pixel decides on its color depending on its integer coordinates. As you may remember, we are trying to reproduce the neuron activation simulation. So let's use texture pixels to represent neuron activations. We need some source of random numbers so that we could activate some of the pixels in the texture spontaneously. There is a convenient hash function that takes three-dimensional vectors of integers and produces three-dimensional vectors of floats. And this is a typical way of obtaining random numbers in shader programming. So we can give it pixel coordinate and some additional number as a seed, and it's going to return a floating point number to us. So numbers are covering range from 0 to 1. We may want to apply a threshold function to those numbers. So this hash function is a part of SwissGL library, but step function is a part of GLSL standard that is used as a shading language here. So we may, for example, activate only a single pixel in 100. I will use JavaScript random number generator and multiply it by some large number. Now texture gets completely refreshed on every frame. But what if we want to preserve some state in it? Well, one option to do this, which works in simple cases, is blending. So OpenGL or WebGL allows us to update the state of a buffer when writing it instead of replacing content completely. So there is a special parameter called blend, and for example, I may say that I need to add the new data to what already exists in the buffer, so source plus destination. And now we will see that new pixels get added to the existing content. Blending is a very limited state preservation mechanism, so there is another way. Instead of rendering to a single texture, we can create an array of two textures and rotate them on every drawing call. So when we render to one, we are free to read from random positions of another textures, which correspond to two different versions of this render target. So there is a special story argument, and we say that we want an array of two textures that are going to be rotated on every call to GLSL that renders to this target. And now we are free to use the previous version of the buffer in computing the pixel color. So for example, we can say that we want a new pixel color to be maximum between the random activation and the value of a pixel to the left of it. There is a special uniform SRC that allows to read from the previous version of the texture. So we are reading from the current fragment position minus 1x. And okay, and we need to say that we are going to read from the specific element of text array. So texture 0 corresponds to the last instance, the last version of the texture. Now we can also multiply this value by some small number so that colors fade out slowly, or maybe subtract some small number. This way we can implement many different simulations and use fragment shader as a general computational mechanism. Let's now slow down the simulation and implement the neuron activation propagation model. First, I moved text buffer creation outside of the drawing loop. So here I create a field and then I simply pass it as a target. So field is still an array of two textures that are going to be rotated in place. I can even look at its contents. So there are two textures. Now updates are triggered only 5 times a second. Now we have everything we need to implement the model from the Artem's video. If we look at the source code he provided, we see that the activation of neurons in a subsequent layer or subsequent column of a texture depends only on the average activation of the previous layer. So we will need an auxiliary buffer in which we will store those average activations. Let's implement it. Let's first create a couple of constants that are going to contain the size of the grid. Now we can create a texture that will contain per column averages of neuron activations. This texture will have size W times 1. And we also need to provide a tag, which we'll call, say, average. And now this rendering pass will read from the last instance of field texture, and we need a fragment program. We'll need to iterate over columns of field. We call the uniform that contains the texture field f. And let me tell a couple of things about accessing textures in SwissGL. So if you look at the library source, then there is the link shader function that receives vertex and fragment programs and generates the shader pair, and this function scans through uniforms that are supplied to a program and generates corresponding uniform definitions in the shader code. And for textures, we have a couple of functions that allow to sample their content, and also there is a couple of helper functions that return the size and 1 over size of a corresponding texture. So there is a helper that allows us to get the size of texture f. So we need to scan across columns. Let's rename this, let's call this variable y. And then we only need the first component of the 4-element vector that is returned from reading the texture in WebGL. So we need to sample at current position x and iterate over y. Now you may notice that previously we used a single line format for fragment shaders, but now we write multiple lines. So if you look at the source code, then there is an expand code function that tries to use some simple heuristics to detect which form of the shader is used. So if the shader code doesn't contain semicolon, then it thinks that this is a one-liner expression and wraps it into the vec4. Otherwise, it substitutes the body. So if it can't find the main function definition, then it tries to wrap the code into a function definition. So this time we will have multi-line expression, multi-line program that will be wrapped in a function. And we need to assign the output somewhere, and there is a special variable called fout, which stands for fragment shader output, and we need to assign the computed value to this variable. So we are computing average, that's why we need to divide by the column length, and we need to cast this to float because in WebGL automatic type conversions don't happen. And hopefully okay, let's visualize this texture, and yeah, if we multiply it by some large number, we can see that now columns, so the texture has a single row, and we may combine two textures together for visualization. Let's show f and say we will show average as red color and the field texture as green color. And by the way, when SwissGL can't compile a shader, it dumps the complete code of the shader with all the tools included and expansions into the console, and we can see that the line at which error happened. So error happened in line 123, and it says that this constructor, vec4 constructor, has too many arguments, and the reason is that I didn't say that I only want the first component of vectors that were returned by texture fetches. So now we see that green texture contains the original field texture, and then those red lines are average values of a corresponding column multiplied by 5 so that it looks brighter. I'm ready to implement the propagation algorithm that Artem used in his video. I only need to compute averages before updating the texture, so I'm moving this code here. Now we see something that looks pretty similar to the model from the Artem's animation. So what I did, I moved simulation parameters into a separate dictionary that just gets added to the parameters that are passed to the shader. And now this is a line where we generate random numbers that we will use later in the code. Here we sample the averages texture from the previous column, and then we compute the output, which is maximum over spontaneous activation of the neuron and activation caused by propagation of the activation probability from the previous column. Now, when we implemented the simulation part, we can proceed to creating a visualization. As the first step, let's make the visualization less chirpy. Instead of showing the state of the texture at the last step, we will smoothly interpolate between adjacent time steps. T is going to be our interpolation factor. Nice thing about storing different states of the system in an array that during visualization we can access multiple states at once. So here F is the last state and F1 corresponds to the previous state of the system. So now we smoothly interpolate between two different system states. We can see it if we slow down the simulation. Right now we render the whole system state as a single quad, but in order to reproduce the animation from the original video, we need to render individual neurons as sprites to be able to shuffle them around. Luckily, SwissGL has a powerful mechanism that allows to render multiple primitives in a single drawing call. That's a combination of using Vertex program with an instance and feature provided by WebGL. So VP is a special parameter that allows to specify the Vertex program that is used during the draw call. By default, GLSL renders a single quad, and Vertex program can store the corner positions of this quad in a variable called vpos, which stands for vertex pos. For example, we can say that the corner positions correspond to what is contained in xy variable, which is the default behavior. If we multiply xy by, say, 0.5, we get a smaller quad. The code of Vertex program will be evaluated 4 times with different values of xy, and this will produce the corner positions for the quad that will be rendered with the fragment program below. For now, let's use UV coordinates as pixel colors. 0, 0 coordinate corresponds to the screen center, and -1 to the lower left screen corner, +1 to the upper right screen corner, which means that if viewport size is changed, then everything gets squeezed or stretched. There is a special argument that alters this behavior. It's called aspect, and we may say that we want aspect fit, which means that -1 box will be fit into the viewport dimensions. So when we stretch the viewport, we see that range from -1 to 1 always visible. We can also use cover argument, which means that the -1 range covers the viewport, or we may say that we want to fix x coordinate. And if you want to look for details how it's implemented, there is calc aspect function that gives different variants for this argument. So we will use aspect fit to make sure that we have same scale for x and y axis. We want to draw a separate quad for each neuron in our simulation. So there is a grid argument that instantiates this quad on a grid of specified dimensions. And we can access the index of the instance using ID variable inside of the shader. So we see that we can easily draw many rectangles instead of one. And here we compute, so now this function is being evaluated 4 times for every instance. And we must compute the coordinate for the corresponding corner. So this is where we position the center of the current quad, the current rectangle, and then here we offset the corresponding corner of that rectangle. Let's now position and scale the grid properly. The grid is now centered, and we may scale each individual sprite according to activation of the corresponding neuron. Yes, we can easily sample textures in Vertex Programs as well. Let's modify the code so that even non-activated neurons are visible as small sprites. Now we may want to change the sprite color depending on activation as well. In GLSL there is a varying mechanism that allows to pass data from Vertex programs to fragment programs. SwissGL offers some helpers so that variants can be declared in line inside of the Vertex program code, so we create a variable with a special modifier. Now we can use this variable in a fragment program. So now brightness depends on the activation. Now I modified the sprite color and also made them a little bit larger. How can we render them as something other than squares, for example as little sparks of light? We can easily do this by modifying the fragment program. So we can easily multiply the fragment output color by some radially decaying function to modulate pixel intensity across the sprite. So I like to use this simple function. Square sprites now turned into bright spots, but if we look closer at them, we will see that adjacent sprites overlap each other, but I would like their contributions to add up. We can do this with a familiar blend parameter that makes each particle to add to the existing image. So new pixel, which is source, will get added to the destination. As a next step, I want to reproduce the neuron shuffling effect from the original visualization. So in order to do that, I wrote a simple function that takes number n and produces the permutation of n numbers. So then I use this function to create a texture that we will use to shuffle neurons in a vertex shader. So I run GLSL command without specifying a shader, and then I say that I need a texture of this size. I want to store numbers beyond 8-bit precision, so I create a 32-bit floating point texture with a single channel. Integer textures are not supported by SwissGL yet. Then I provide the tag, and I provide the float 32 array that contains the data. So for each pixel in the texture, we will have an integer number, and those numbers will be shuffled for all neurons. Let's now look at the modifications to the rendering code in order to shuffle neurons between the grid state and the random circular arrangement. So I created a phase variable which depending on time slowly changes from 0 to 1. I pass this phase to the shader. Also, I made a shuffle texture available to the Vertex program. And the first thing I do, I sample the current sprite, current neuron shuffled index from the texture. And then I compute two positions for each point, for each sprite. First position is our original, that depends on the grid coordinates, and the second is the position in a shuffled circle. So instead of depending on sprite ID, I depend on its shuffled index. And then instead of using the square arrangement from the Artem's video, I went on with golden angle based arrangement that is often used to describe the placement of, for example, sunflower seeds in a flower, and it involves rotation by so-called golden angle, which is close to 2.4 when expressed in radians between each when adding each new point. So this arrangement, I compute the current angle, and also I compute the offset vector from the center, which depends on a square root of point index, and then I rotate this vector by the given angle. So this rot2 function takes angle in radians and produces 2x2 rotation metrics. Actually, if you want to look at other helper functions that are available in SwissGL, then there is a GLSL template constant. This is where your snippets get substituted, and there are a few functions that I added there, like hash that is commonly used, two-dimensional rotation, and some others. maybe I'll add more functions in the future. So, and now I have grid coordinate, I have shuffled point coordinate, and then I just interpolate between those two coordinates depending on the current visualization phase, and add the sprite corner offset. When we animated the point positions, the last missing piece of the visualization is decorative graph edges that express the connections between neurons. In order to draw the edges, we will need a separate draw call in addition to sprite rendering. So I modified the code in a way that will simplify rendering edges, because rendering edges would require knowing node positions that are computed in a sprite rendering path. That's why we will need to share snippets of code and uniforms between two render passes. To do that, I usually do the following. I create a common dictionary where I put all uniforms, parameters that are shared between render passes, and then include this dictionary into the dictionary that is passed to GLSL function. And also there is a special include argument to GLSL that allows to provide text snippet that gets included to both fragment and shader program, and this is convenient way to pass functions that are required in multiple shaders. So I wrote a function node pos that takes index of the node and computes position of this node depending on the phase. So it computes both positions, interpolates between them, and returns two-dimensional point where the node is located. And then vertex rendering vertex shader gets simplified to calling node pos function and adding the corner offset. Now we are ready to implement a separate render path for edges. Edges will be drawn before points so that points are on top. Note that we will add edges for illustrative purpose only, so they will not participate in simulation itself. That's why we can simply generate them on GPU entirely without even building any CPU side data structures. All we need is a single call to GLSL function. We will use some common parameters we defined before. Then I will create a single edge for each vertex except vertices of the last layer. So I will create a grid, and I will need a vertex program and a fragment program. Fragment program is going to be simple. I will just emit some grayish color. And vertex program is where all the magic is going to happen. Each edge is going to connect one node from the current layer with the randomly chosen node from the next layer. And now we need to set up vertex positions for the quad. Quad is going to be constructed on top of two vectors. So one vector is just the one that points from first vertex towards the second. And another vector should be orthogonal to it. So let's create a vector that is going to be orthogonal to the vector connecting two points. We can do it, for example, this way. Let's first create a unit vector pointing from point 1 to point 2. And then rotate it 90 degrees. let's call it n, and then we can simply add this vector to point coordinates. We now see that every point is connected to some randomly selected vertex from the next layer. Let's freeze the phase animation for now and look closer. So let me explain what this code does. This is the offset, the magnitude of the offset that we apply to vertices in the direction that is orthogonal to the direction to the adjacent vertex. So this way we can modify the width of lines, make them wider or thinner. We can generate graph-like visualizations without ever constructing the actual graph in memory, and GPUs are really fast, so I suspect that this computation, this way of constructing visualization networks is faster than making some lookup tables and fetching data from memory, although I didn't benchmark it. But also we may want to make edges semi-transparent, and let's use blending to achieve this. So this is additive blending, but let me show the like standard way of doing blending when layers overlap each other and each primitive has some transparency that depends on its alpha channel. So this is the standard way to render semi-transparent primitives. Well, I guess that's it. Let's add a little bit of interactivity so that transition between phases happen on mouse clicks. I now added some interactivity. Let me go through changes I made to the code line by line. First, I added a couple of helper functions. One simply clamps input parameter x to the IA to B range, and then smooth step to make linear transitions a bit nicely animated. Then I added a phase variable that corresponds to the current transition phase, and you see I made it clip to 0.1 instead of 0 by default, so that vertices are not perfectly aligned on the grid, because I think it looks a little bit nicer. And then this is the rate of change of phase, whether we are going to disk arrangement or layer by layer arrangement. And whenever I click on the canvas, I simply reverse the direction that phase is currently changing to. And then I added some comments so that we see what every rendering call we implemented is doing. So far we implemented 4 rendering calls. One to compute average activations, second to propagate activations, and then here I compute the difference of time between last and current frame and update change to the phase. But when I pass phase to the rendering function, I apply a smooth step to it, so the transition is not linear, but points slow down, like start up slowly and then slow down in the end a little bit. Then this is the edges rendering path, and this is nodes rendering path. And if you look at the console, then we can see all the objects that SwissGL created to run this program. So this is the auxiliary buffer that is just workaround to broken vertex ID and primitive and instance ID support on some WebGL implementations. Then there are two field textures, each of which has a corresponding frame buffer object. This is a shuffle texture, which doesn't have frame buffer because we never render to it. Then there is average texture with a corresponding frame buffer. And then there are four shader programs, each of which is a vertex and fragment shader pair, that were created to implement our four draw calls. And we see that it all took us around 80 lines of code, including all the HTML and some comments. And of course, we were operating at a very, very low level here. And although this may sound a little bit inconvenient, but I think there is some value of being that level, because we retained full control on every aspect of our visualization. For example, if I'd like to tessellate edges and make them not straight lines, I can do it here. I can alter every aspect. And still, I think the amount of code I had to write to implement this effect is comparable to amount of code I needed if I used some set of libraries. I tend to think of SwissGL as not a library, but rather a point of that maybe inspire more people to to program in a minimalistic way without accumulating many dependencies, because often when you start developing something, external libraries accelerate the progress, but then at some point I always found myself that there is a stage where I'm fighting against the library because I'm trying to do something that wasn't originally intended by library developers. So that's all I have for this presentation, and thank you. I hope you find this interesting and useful.